Welcome to In 5 Minutes. We will now discuss frequency modulation parameters. We will define few important parameters. For example, modulation index, something that we had also defined for amplitude modulation signal, and few more parameters which are used in the analysis of FM and also for PM signals. So because we are discussing parameters for frequency modulation first, I will start with the FM signal. Just now we have written the expression of FM signal. It goes something like this: Vc cos omega ct plus 2 pi kf is nothing but a constant, and you have integration of m of t. So we have integration m tau d tau, where tau is the dummy variable and t is the actual time variable. Now let us consider some modulating signal. Whenever we do analysis, to simplify the analysis and to understand the nature of modulated signals, we consider m of t, the modulating signal, to be single frequency sinusoidal signal. That is what we had done in case of amplitude modulation also, and we will repeat it for FM and PM. So let me take m of t as Vm cos omega mt, where omega m will further be equal to 2 pi fm. Fm will be modulating signal frequency in hertz. Omega m is written in radians per second. Vm is the peak amplitude of the modulating signal. So if this is my m of t, let us put m of t in this above expression. That means let us integrate m of t and put it in the expression and see what do we get. So before we go to the actual expression, I will integrate the given m of t, the m of t that we have considered. Now when you integrate the m of t in the form of a dummy variable tau, you can see Vm is a constant, so it comes out. Now because cosine signal is a periodic signal starting from minus infinity up to 0, let us assume that we have covered the integer number of cycles of the signal. And when you integrate over one cycle of cosine signal, the positive and the negative half integrations will cancel out each other, and hence the integration will be 0. So starting from minus infinity will be as good as starting from 0 and going up to t. And I'm going to integrate cosine function, which is written as a function of a dummy variable tau. When you integrate this, integration of cos becomes sine. And when you integrate any function, you have to divide by the coefficient of the variable, which in this case is omega m, and the integration will be nothing but sine omega m tau, and we will consider the upper limit as t and the lower limit as 0. If you put the limits, you can see upper limit tau will be replaced with t, and when you put lower limit as 0, we know that the sine of 0 is equal to 0, so we get Vm upon omega m into sine omega m t. Finally, my actual FM expression becomes Vc, which is the peak carrier amplitude, into cos omega ct. Omega c will be 2 pi fc, where fc will be carrier frequency in hertz, plus 2 pi kf into, you can see I'm now replacing for integration of m of tau d tau, which is nothing but Vm upon omega m into sine omega mt. Further, this expression becomes Vfmt equal to Vc cos of omega ct plus, I will replace omega m with 2 pi fm. So that 2 pi and this 2 pi will cancel out. So I'll get kf Vm upon fm into sine omega mt. I'm going to make one very important substitution, which we will define later on. I'm saying let kf Vm upon fm. You can make out that it's a constant for given modulating signal. Kf was a constant. Vm and Fm are the values associated with modulating signal. So for the given modulating signal, this whole thing will be a constant. I'm replacing it with a notation mu suffix f, where mu f will be called modulation index of Fm. We will define it properly. This is one expression, kf Vf Vm by Fm, for modulation index. We will again define it using another expression. I'm attaching suffix f for Fm. We will define mu p, which will become modulation index of Pm. So after this substitution, we get Vfmt. My Fm signal simply becomes Vc cos of omega ct plus k Vm by Fm is nothing but mu f into sine omega mt. So please remember this as one very important standard expression, where my modulating signal is single frequency sinusoidal signal taken in cosine form, and that gives me a standard expression for the FM signal, which looks something like this. The coefficient of sine term here is mu f, and that represents nothing but the modulating signal.